All right. So, and so therefore this is a low pass transfer function. What comment can we make about this transfer function here? What comment can we make about this transfer function? Okay, so this is VLP of S. Right? What is this transfer function? Yeah, we know VLP of S. So what should this be? What is the transfer function of this from here to here? What is the transfer function? Minus 1 by SCR. So this transfer function must therefore be VLP of S times minus SCR. Right? So that's basically S by omega naught divided by 1 plus S by omega naught Q plus S square by omega naught. What kind of transfer function is this? At DC, it's evidently 0. At infinite frequency, it is. As S tends to infinity, what happens? It goes to 0, right? And somewhere in the middle, it basically peaks. So this is a band pass transfer function. Is it inverting band pass or non-inverting band pass? Non-inverting band pass, right? So this is say VBP of S, and what therefore must be the transfer function here. So we've seen what this is. We have seen what this is. What is that transfer function? Well, this is nothing but an inverting amplifier. So this is basically minus VBP of S, right? So looking at the voltages at different points in the circuit, it's possible to you see that we get both low pass and band pass responses, right? In our example, we are only interested in the low pass response, so our final output will be the LP of S, right? And recall, as you can see in the picture there, it's an inverting low pass response, right? And so now, as I said, this is what is called a biquad. Okay, and which is just slang for biquadratic section. Now, if you want to build a high order filter, therefore, what do you do now? Well, cascade a whole bunch of these things, right? And can we make any comment on the parasitic sensitivity or insensitivity of this structure? Let's say every capacitor is associated with some parasitics to ground, right? What comment can we make? Well, all parasitics are either at virtual ground or the output of an op amp, and therefore, just like in the first order section, right, the whole structure is insensitive to parasitics. And this is extremely important in practice because remember that the idea is to have filters, on a you have a big SOC, for instance, where you have filters. The output of the filter goes into an A to D converter, and then you have a DSP, and the DSP is basically a lot of digital circuitry, correct? And they're all sitting on the same silicon substrate, right? So what happens therefore is that the digitals, the digital circuitry basically can cause a lot of what's called ground bounce, right? Simply because you know that a CMOS inverter basically draws a big spike of current from the supply to ground at every clock edge, right? Whenever the input data changes. Okay, so there's basically a lot of junk on the ground, and therefore if ground is not, and if you have a structure which is sensitive to parasitic capacitance, then through that ground which we thought was ground is not really ground, and therefore can can inject noise into the filter and so on. So parasitic insensitivity is actually a very useful and important attribute in practice. Of course, there's also an issue of robustness in the sense that when you have parasitic capacitances, you basically are not in a position to exactly predict the omega naught in Q, simply because if you have some stake capacitances which modify the integrated transfer function, then you have you don't know what omega naught you're getting and what Q you're getting, and therefore there is again a problem with respect to robustness. Now, a couple of points that I'd like to draw your attention to, right? We'd like to make sure that there is negative feedback. Remember, the difference between the input terminals of the op amp is 0 only if there is DC negative feedback around the op amp, right? And the question is, is there a DC negative feedback around each of these op amps, right? So for example, let's take a look at the last op amp. For DC, the capacitors are open, so I'm going to remove that. Okay, and I break the loop. All right. So if I yank this side up, if I yank this side up, what happens to this voltage? Hit. I mean, well, we assume that the other op amps are in negative feedback. So if that goes up, what happens? This goes down. If this goes down, what happens to this voltage? Goes up. If that goes up, and we've assumed these signs, so what happens to the output of this op amp? What happens to this output? Goes down. Right. So is there negative feedback around this op amp? Yes. Right. So likewise, you can go and do this for all the op amps. And when you come up with a new circuit, the first thing you should check and make sure is that you choose the signs of the op amps properly, so that your assumption of the virtual ground remains within ports, is actually valid. Does it make sense? All right. So that is that's one thing that you have to be aware of. The next thing that I'd like to draw your attention to is the following. So let's say all these resistors are scaled up by the same factor. In other words, I multiply all resistances by alpha. Now we seem to be missing the capacitors. Right? All resistors are scaled up by alpha. What comment can we make about the transfer function? Pardon? All resistors go up by alpha. Then earlier, let's say you had a transfer function h of s. Now what happens to h of s? What happens to q? Well, q is remains the same because it's a ratio of like quantities, right? It's dimensionless, so it doesn't change. What about omega naught? Omega naught is 1 by RC. All resistors have changed by a factor of alpha. So the omega naught goes down by a factor of alpha. So what happens to h of s? Very good. This is h of alpha times s. Alright. Now so if all resistors remain the same, but all capacitors go up by a factor of alpha, what comment can we make? What happens to Q again? What happens to the quality factor? It remains the same, right? Again, the idea being that Q is a dimensionless quantity. If all capacitors are increased by the same factor, then you will get. So what happens to omega naught? Comes down, right? So what happens to HFS? HF alpha, right? Okay. So now I'm going to ask you the third question. I increase all resistors by a factor alpha, decrease go down by a factor of alpha, right? What comment can you make about the transfer function? Well, we can do this in 2 steps, right? All resistors go up by alpha, you basically get H of alpha S. All capacitors go up by a factor of 1 by alpha. So, H of alpha S times 1 by alpha. So, you basically nothing changes. Correct? So, now the question is, what have we achieved by doing this? Right? It seems like if you increase all resistors by a factor alpha and all capacitors are reduced, you have the same transfer function. Right? So, what do we gain by doing this? I mean, is there any practical advantage to increasing all resistors by a factor of alpha and reducing all capacitors by a factor of alpha? Well, capacitors all become small. So, and as you know, on an IC, capacitors are parallel plates that are planar, and therefore, if you make the capacitors all smaller, evidently the filter itself will become very small, right? There is a further advantage in the sense that if all resistors increase by a factor of alpha, what comment can you make about the currents through the resistors? Well, if all resistors increase by a factor of 10, all currents through them go down by a factor of 10. Now, if all currents go down, and who is actually supplying these currents? The op amps are basically supplying these currents, correct? So, if all currents in the resistors go down by a factor of alpha, then the op amp's job becomes much easier because it has to supply a much smaller current. If the op amp needs to supply a much smaller current, remember that an op amp inside is made with transistors. Transistors have to be biased, and the current that's coming out of the op amp is within quotes the incremental current, right? So if you need a much smaller incremental current that the op amp has to supply, what comment can we make about the bias current itself? Remember that the increment is supposed to be a small fraction of the quiescent current. If the incremental current that you are supplying needs to be much smaller, then we can basically the bias currents in the active devices inside the op amp can also be correspondingly small, right? So increasing resistance and reducing capacitance has two benefits. One is of course the area occupied by the entire filter, which is predominantly that occupied by the capacitors, becomes fundamentally smaller, right? And second, since the op amps now have to drive supply currents which are much smaller, it means that the quiescent current that they can dissipate, right, also becomes much smaller. For instance, if the incremental current became smaller by a factor of 10, let's say we increased all the resistors by a factor of 10, then the incremental currents or the currents that the op amps need to supply go down by a factor of 10, right? Which in principle means that the quiescent currents can also all go down by a factor of what? By a factor of 10, correct? So doing this basically reduces area by a factor alpha. It also reduces what else? Quiescent current, and quiescent current is related to the power dissipated, because that's the total power dissipated is simply the sum total of all the quiescent currents in the op amp multiplied by the supply voltage. So this also reduces power dissipation by a factor of alpha. Correct? So this seems to be a great idea. All right. So what would you do? So what is the obvious thing to do? Therefore, so choose alpha to be as large as possible, which is equivalent to saying make the resistors larger and larger and larger and larger, and the capacitors become smaller and smaller and smaller. Right. So in the limit, we'll have a filter that occupies no area and dissipates no power. Right, because alpha tends to infinity, evidently the currents in the resistors tend to 0, right, and therefore the power dissipated in the op amp can also in principle tend to 0, and the area occupied by the capacitors obviously tends to 0 because I am decreasing the capacitors, right. The transfer function evidently remains the same because that's what we discussed, right. Okay. So it seems like you can get away by having 0 power, 0 area, and the same function, right? So there is I remember one thing, something that sounds too good to be true, right? Is often something that sounds too good to be true is often really too good to be true, right? So there must be a catch. We must be missing something. Right? I mean, this sounds exactly like give me your money and I'll double it in in 2 minutes, right? Okay. I mean, I hope none of you is naive enough to believe it. Yeah, Jishnu had a point. Yeah. Well, yeah. I mean, he says as you keep increasing resistors. Right, the resistors can in principle tend to get bigger, but that's not a fundamental problem. It's it's basically, I can to get a larger and larger resistance. What can I do? Well, make it thinner, make the wire thinner and thinner and thinner. I mean, at some point, of course, there will be a physical limit to how thin you can make this, but it's not a fundamental limit. Right? In principle, I can make something an angstrom thick, and then I get infinite resistance. Right? Okay. All right. So as you can see, therefore, there's something that we are missing, right? Something fundamental that we are missing, because this whole premise sounds too good to be true, right? And what we are missing is, it turns out that the resistors also add noise of their own, right? And therefore, the output of the filter consists of two parts. One part is the input signal which has been filtered. The other part is each one of these resistors is adding noise, right? And that kind of from each resistor to the output there is some transfer function, right? Therefore we have to the output will not only consist of the filtered input but also noise from the filter itself, right? And it turns out that as the resistor becomes larger and larger, it adds more and more noise, and the output noise of the filter becomes larger and larger, right? So therefore, indeed there is a catch, and if you go on making the resistors larger and the capacitors smaller and hope that you can do the same job with fewer and fewer resources, you're going to be terribly mistaken. So that will that's motivation to go and study noise, which we'll do a few classes down the line, right? But that's something that you need to bear. And this process where all the resistors have increased by a factor alpha and all capacitors have decreased by a factor of alpha. What is the, decreasing the capacitor of alpha, what does it do to the impedance? Remember, that the impedance of the capacitor is 1 over SC, and it's become, if you reduce the capacitor by a factor of alpha, it now has become alpha over SC, and therefore, as you can see, doing this is equivalent to scaling all impedances by the same factor alpha. So, if you take an electrical network and multiply all impedances by the same factor, what comment can we make about the transfer function? Remember, a voltage transfer function basically is a dimensionless quantity and must be therefore a function of ratios of like elements, right? And therefore, the transfer function doesn't change, and so this is what is called impedance scaling, and that does not change the transfer function. Alright, what does it change therefore? I mean, if it doesn't change the transfer function, what does it change? We just discussed this, a few minutes back. It changes. It turns out that it changes the noise produced by the filter itself. Okay, which we'll have an opportunity to study in great detail. A little down the line, right? But you shouldn't go away with the impression of saying, oh, let me go and increase all resistors and reduce all capacitors, by a factor of 2 million, and then therefore, I have a tiny filter and it does the job. Okay. So, thank you and.